In this video, we are going to talk about indented paths and how we can use indented paths to integrate around a branch point. This is our overview slide, which we'll spend about 5 minutes going over before we go over each topic in more detail and with more examples. The first thing we'll talk about are indented paths. We'll define them and also use this theorem that suppose we have a function f of z that has a simple pole, z equals x naught, on the real axis. So here we have the real axis and here we have x naught, which is a simple pole. And it has a Laurent series representation in a punctured disk. So a little disk around x naught, if we ignore x naught, we could say that there's a Laurent series representation in that punctured disk and with residue B naught. If CP then denotes the upper half of a circle where z minus x naught is equal to p, so in other words, this upper half of the circle here centered around x naught with radius p, where p is less than r2 and with the clockwise direction taken, then the limit as p approaches infinity of Cp f of z dz is equal to minus pi I times the residue B naught. The next thing we do is look at how we can use these indented paths to evaluate improper integrals with singularities along the real axis. So an example would be the integral from 0 to infinity, and this infinity here makes it an improper integral, a sine of x over x dx. This problem is very similar to the one we did in our last video with improper integrals. However, this here has a singularity along the real axis. In our last video, when we talked about using residues to evaluate improper integrals, we assumed that there were no singularities along the real axis. So this sort of completes that topic because now we can deal with singularities along the real axis. We follow a very similar method or approach that we did for improper integrals, and that if we're talking about integrating along the real line, and in this case from 0 to infinity dx, this means the values that we are looking at on this function are only real values. So as we integrate along the real line, what we can do is create this closed curve. In our last video, we would just add this semicircle on top of our real line. But now we have the singularity, and in this case at x equals 0. So what we do is we make this little indentation, this indented path represented like this CP from our theorem. Then the approach we will take are from these 6 steps. We replace f of x by f of z. So in other words, we extend this function, so now we can talk about it as a complex function. However, the values of this function along the real line remain the same. So it's just an extension of this real function, real values, but now we can plug in complex values. We note the singularities on the real axis. In this case, it would be x equals or z equals 0. If there's any sines or cosines, we replace sine with ax or cosine ax with e to the I az. We make this closed contour integral and we apply the Cauchy-Gorsatz theorem since there are no singularities inside the closed curve, because now we add this little curve, this indented path that goes around our singularity. The Cauchy-Gorsatz will say that the sum of our path, or the integrals along our path, will sum to 0. So we integrate around CR, and as r approaches infinity, that will equal to 0. And by our indented path theorem, our integral around CP will equal to I pi times our residue. And finally, if our integral had a sine in it, sine of ax, we'll take the imaginary part of our final answer for our answer. And if it had a cosine in here it's sine but not cosine, but if it had cosine, we would take the real part. We are going to use a similar approach to handle indentation around a branch point. This is the example we will be doing in this video, and it involves a logarithm which is multi-valued because it has the same value every 2 pi I times whatever integer n. So what we're going to do is use a branch cut, so we limit our theta now. Instead of going around and around multiple times, it's going to only go from negative pi over 2 to 3 pi over 2. So only from negative pi over 2 over here to 3 pi over 2. So it's only one circle, and that'll give us a single function for our natural log. But what we need to do is then avoid this branch point of 0, or the origin, which is part of our branch cut, because let me put our branch cut in red. We'll be using these 5 steps, which are very similar to what we did in our improper integrals with singularities. The first thing is we're going to replace f of x by f of z. Second, we will note the singularities, and here we're actually going to have a singularity inside our closed curve. So when we make our closed contour integral, we can no longer apply Cauchy-Gorsatz because there is a singularity here, but what we will apply is the Cauchy residue theorem. And the Cauchy residue theorem then says the integral around our closed path, which is composed of L1, C sub r, L2, and C sub p, so these 4 paths gives us a closed path, is equal to 2 pi I times the residue at a singularity of f of z. The next thing we will do is show the integral around C of r approaches 0 as r approaches infinity, and the integral around C of p approaches 0 as p approaches 0. And to do this, we're going to use the upper bound for moduli of contour integrals theorem. So we'll find that this integral and this integral, both of the semicircles, go to 0. And finally, we will equate real or imaginary parts. Before we continue our overview, I did want to write out in full the Cauchy-Gorsatz theorem, the Cauchy residue theorem, and Jordan's lemma, all 3 which I had mentioned in our previous slide, and we will be using on nearly every example. So first, actually I should back up and say we have this indented paths theorem. That one's new, and right after our overview, we're going to take a closer look at the indented path theorem. The Cauchy-Gorsatz theorem you've already seen, or we already had a video about, but just to review, if function f is analytic at all points interior to and on a simple closed contour, then the integral around the closed curve is equal to 0. The way we will be using that is we'll be looking at this contour here. So it includes the real number line. It's going to include a semicircle over the real number line. It has our function f of z has a singularity at this example at 0. So what we're going to do is we're also going to add this little contour, the semicircle that goes right around 0, and we're going to take p, the radius of this little semicircle, to get closer and closer to 0, so that this circle becomes infinitesimally small. But you can see then we'll have a closed contour integral, and if f is analytic at all points interior to and on the simple closed curve, so in other words, in this yellow portion, and this also includes on the closed curve, so we're analytic, meaning there's no singularities in here, then that means the integral along the entire curve, and in this case, the curve is made up of the straight part L1, the semicircle CR, the straight part L2, and the semicircle CP will equal to 0. The Cauchy residue theorem is very similar in that we are going over a closed contour. However, now we're going to handle the case if we have a singularity inside the closed contour. So let C be a simple closed contour, positively oriented. If a function is analytic inside and on C except for a finite number of singular points inside C, then the closed contour integral is equal to 2 pi I times the residue of all of our singular points. And the way we'll be using it, again, using this indented path. We have the real number line with the indented path, this little semicircle that goes around our singularity 0. We have the semicircle going on top. So our path consists of L1, CR, L2, and CP, and we possibly have In this case, I showed one singularity. So the closed contour integral around this path is going to equal to 2 pi I, in this case, the residue at z1. Finally, we have Jordan's limit. Suppose we have a function f of z that is analytic at all points in the upper half plane that are exterior to a circle of radius r naught. So in other words, all points in the upper half plane exterior to the circle. So we're analytic everywhere out here. And here is our circle of radius r. C sub r now denotes the semicircle. And if we're integrating along C sub r, so for all points z on C sub r, if there's a positive constant m sub r, such that this m sub r is a maximum value of the modulus of f of z, and as r approaches infinity, in other words, our real number line, we're integrating from negative infinity to infinity, then for every positive constant a, the limit as r approaches infinity of c sub r, f of z e to the iaz dz is equal to 0. So in other words, if we have a function of the form f of z e to the iaz, and we're going to use e to the iaz whenever we have a sine or cosine. So if we have a function of this form and we're integrating over the semicircle, as the radius r goes to infinity, then our integral along the semicircle will equal to 0. Okay, now we've concluded our overview, we can go back and take a closer look at indented paths. I have this theorem here for indented paths, and the first thing I want to focus on is the definition of this punctured disk. And this is something I have discussed in previous videos, but in case you haven't watched that video or maybe need a review, let's talk about the definition of a punctured disk, which we do down here. And the idea is I have the singularity at x naught, and I want a punctured disk around this point x naught. What we're going to do is start by talking about a circle of radius r centered at x naught. So let's just say the distance between x naught and this point on this dotted circle is equal to r. Then our circle of radius r centered at x naught, we can write this equation for that we want all the points z such that the distance or the modulus between z and x naught is equal to r. So that's going to be this dotted circle here, the one that I'm outlining in yellow, and I'm just going to underline circle of radius r centered at x naught, and maybe the equation as well. So this is the equation and what we call the circle of radius r. Now, what if we want to talk about the interior of the circle? So the interior of the circle is what we call the disk, and the equation for that now is the distance between z and x naught is going to be less than r. I wish I had an orange color. Maybe I'll do this in green. So that's everything inside the circle, because the distance between the point here and x naught is smaller than the radius, right? The distance between this point and x naught is smaller than the radius. And that definition is the disk. The disk is essentially the interior of a circle. Finally, what if we want to eliminate from this disk our point x naught, our singularity? The last thing we would need to do then is essentially just eliminate the point where the distance between z and x naught is equal to 0. Essentially, that's going to eliminate this one point. Actually, I'm going to dot it in red, because just think of if I could put a little pinprick and just eliminate that point. And that then, this interior of the circle, excluding this one point x naught, would be our punctured disk centered at x naught with radius r. Now we can look at our theorem for indented paths. The reason why we call it indented paths will be more obvious later like in our next slide or two. But for now, we're just going to say it's for an indented path. Suppose we have a function f of z that has a simple pole, z equals x naught on the real axis. And this point here, that it's on the real axis, is the one that differentiates us from our previous video when we talked about indefinite or improper integrals along a real axis. In that video, we assumed there were no singularities on the axis. So this is the video that kind of takes care of singularities on the real axis. So suppose we have a function f of z with a simple pole, z equals x naught on the real axis, and that function f of z has a Laurent series expression in a punctured disk. And so in some neighborhood or some small circle around x naught, not including x naught, and with a residue at b naught. So our singularity has residue b naught. If Cp now denotes the upper half of a circle, which we'll have here, which is z minus x naught equals p, where p is less than r2 and in the clockwise direction, then the limit as p approaches 0. And so in other words, we're going to take this radius smaller and smaller till it just barely surrounds x naught. The limit as p approaches 0 of our integral around Cp is now going to equal to negative pi I times the residue of our singularity x naught. So now why is this called an indented path? As I had mentioned in a previous video, we had integrated improper integrals of functions that had real values plugged into them. So along the real number line, we would integrate from x equals, for example, negative infinity to infinity. The thing about our previous video is we could not handle singularities on the real axis. So we just assumed we could integrate along the real axis with no problems, no singularities. But now we're taking the case where there is a singularity on the real axis. So what we're going to do in this case is we'll integrate along the real axis from negative infinity to infinity, but we'll make this little indentation, what we'll call our indented path, that kind of makes a small semicircle around our singularities. And we're going to take the radius of this circle to, in the limit, to approach 0. So essentially, we're going to be integrating along the real axis. And what our theorem is going to tell us is as the limit approaches 0, our integral along this little indentation in our path is going to equal to negative pi I times the residue of our singularity. So let's do an example. Our first example for application of indented paths are improper integrals with singularities along the real axis. The example we will do is to integrate from 0 to infinity sine of x over x dx. And these are the steps we are going to use to accomplish this improper integral. I have moved those 6 steps up here for our reference, and here is our first example problem. Step 1 is to replace f of x by f of z, and step 2 is to note the singularities on the real axis. So I've done this here. I replaced our x with z, and then I noted there's a singularity at z naught equals 0. So replacing x with z is here we have a function of real variable x, but we can extend that function to complex variable z. So x, even though it's on the real number line, it's still a complex number. It's just a complex number where the imaginary part is equal to 0. So what we're going to do is, again, extend this real valued function to a complex valued function, but when we plug in real numbers for z, we're going to get the same values we would get for sine of x over x. So we've done the first 2 steps here. We identified our singularity. So the third step is to replace sine of ax or cosine ax with e to the iaz. In this case, the a is equal to 1, right? The multiplier of our variable is just equal to 1. So we're going to replace this sine of z with e to the iz. And we still need to have this 1 over z factor here. The next thing we want to do is make our closed contour integral. It's going to consist of 4 parts: a straight line L1, a semicircle CR, another straight line L2, and another semicircle CP. And here is the closed curve we are going to construct. So you can see we have this little indentation that goes around our singularity z naught equals 0. and our radius is going to be P for this semicircle CP. And then again, if you remember, we're going to take this CP approaching 0. Here is L2 and L1 along the real number line. L2 and L1 go from negative R to negative P and P to R. We're going to take R approaching infinity, so essentially that will give us our real number line, and the negative P approaches 0, so we come all the way up until we barely, just touch our singularity, and then on the other side, this P is going to 0, so we have the straight line, and this R over here goes to infinity, so that kind of gives us our real number line portion. And then finally, we have this semicircle above of radius r also going to infinity, and that closes off our curve. So we have our closed contour consisting of our 4 points, our 4 parts, L1, CR, L2, and CP. And here are just some of the notes about our closed contour. P and R are both real numbers because they represent radiuses, and P is less than R, so the radius of our little indentation has to be less than our big contour that kind of encloses our whole closed contour. L1 is the interval from P to R on the real axis, so from P to R, and again P goes to 0 and R goes to infinity, so that's like the positive part of our real axis. L2 is the interval from negative R to negative P, so over here that'll give us the negative portion of our real axis as negative R goes to infinity and negative P goes to 0. And then CP, again, is used to avoid passing through the singularity. It's our little indentation that goes around our singularity. I'm going to make some room by first shrinking and then moving our closed contour here. And I'm also going to make some notes. These notes are general notes that we're going to use in like so many of our, and actually almost all of our problems that are of this type. And I have this here in our overview up here. But essentially, this is what our closed contour will look like for step number 4. And it looks like L1, that's this first integral, CR, L2, and then CP. And because in this example there are no singularities inside our closed contour, so this is important, there are no singularities inside the closed contour, so we're going to use the Cauchy-Gorossatz theorem that says if a function f is analytic at all points interior to and on a simple closed contour C, then the integral around the closed curve is equal to 0. So we're going to set the integral around this closed contour equal to 0. And again, just pay attention. Here, the f is analytic at all points interior to and on the simple closed contour. So it's analytic on the contour and everywhere inside. In other words, there's no singularities on the contour, there are no singularities inside. So we can use Cauchy-Gorossatz, set the entire closed contour equal to 0. And that will be our step number 4, which is to make a closed contour and apply Cauchy-Gorossatz. Coming back to our example problem, the first thing is we replaced x by z. We noted the singularity at z naught equals 0, and we replaced sine of x here with e to the I z. So plugging in now into our closed contour and grouping our L1 and L2 together, moving our CR and our CP to the other side of the equation then, we're going to have the integral over L1 e to the IZ over z dz plus integral over L2 e to the IZ over z dz is equal to negative integral over CP e to the IZ over z dz minus the integral over CR e to the IZ over z dz. At this point, we've done step 1, step 2, step 3, and step 4. You'll notice step 5 starts talking about the C sub r and C sub p. That's this side of the equation. I guess I probably should have put one more step in because we need to look at the left-hand side of this equation. That is when we're integrating along L1 and L2. Right here between step 4 and 5, we're going to look at the integral on L1, which is over here on this part of the real axis, plus the integral along L2. We'll start by parameterizing L1. Actually, the first thing I want to do is looking at L1 is to realize that any complex number z on L1 has phase or has angle equal to 0 because we're right on the real axis. There's none of this, angle of theta associated with z. It's on real axis, so our theta is equal to 0. So when we write our complex number in exponential form, our z is equal to r, our radius, times e to the I 0, which e to the I 0 just goes to 1. So z is equal to r, and our values of r now range from p to capital R. L2, on the other hand, when we look at L2, our value of theta then becomes pi, right? Because we actually have to go around to get to this negative part of our real axis. So z is equal to our radius r, e to the I pi. E to the I pi becomes -1, so z is equal to -r. And here r, the value of r, goes from negative r, we're integrating along L2, it goes from -r, and then L2 goes towards 0, but only up to -p. The thing is I want to combine these two integrals, and it's easier to combine them if I can just add the integrals together. I can't do that right now because the limits of integration for L1 are going to go from p to r, and from L2 the limits of integration go from -r to -p. What I would like is to convert my integral so that my limits of integration for L2 also go from p to r. What we are going to do then, I have my integration for L1 on line 1, e to the I z over z dz, plus my integration on L2, e to the I z dz. I'm going to consider integrating in the opposite direction along L2. In other words, I'm still going to integrate along this line, but instead of going from -r to -p, I'm going to go in the opposite direction. I'm going to go from -p to -r. And from calculus, we know when we integrate from a to b, that's equal to the negative of integrating from b to a. And also in vector calculus, even if you have some path that's not just a straight line path, this is also true, the path in the opposite direction. In this case, it's not even a line path integral, it's along the axis. So since we have this negative sign here for when we go in the opposite direction, so this will give us this equivalent of going to L2. So now I have my L1 integral minus, and then we're going to go from -p to -r. Since our function e to the I z over z here is odd, I can plug in p and r instead of -p and r, and then all I need to do is change this to a plus sign. And I have kind of these notes in blue here to remind ourselves, if we have this integral from -p to -r, I take the antiderivative evaluated at -r minus antiderivative at -p. But again, if our function is odd, this here is equal to f of p minus f of r, which is the integral from p to r, f of z dz. Now I'm going to substitute my r for z, so I'm going to integrate over r. So on L1, again, that already goes from p to r, e to the I, and on L1, z is equal to r. So e to the I r over r, and then dr is just equal to dz. For L2, now we're still integrating from p to r, but on L2, z is equal to -r. So this is e to the minus ir over minus ir. And then the other thing we need to know then is that since z is equal to -r, dz is equal to -dr. So now I need this negative sign would become a positive sign. Actually, after all that work, I just realized I had converted this limit of integration, it wasn't incorrect, but I did it really the painful, hard way because that's what had first occurred to me. But really, if what I had done is I converted my function, my f of z, into a function of r, and then just said I'm going to integrate with respect to r, dr over here instead of dz, then I could have said r is a positive number because it represents a radius, and the radius ranges from p to the larger value r. So that would have gotten this this change, this kind of integration limits automatically to this form. So I wanted to show you both though, because the other way is what first occurred to me, and if that's how you look at it, I wanted to show you you could get to this form here. But you know what? In the future, I'm just going to go directly and say I'm integrating with respect to r, and just say that my integration for L2 goes from p to r, because r is always a real number, so it's going from the smaller p to the larger capital R. Now I have both my limits of integration p to r. I have my e to the I r dr, taking this negative sign out here, minus p to r, e to the I r dr. I can combine these two under one integral using this formula here, that sine of z is equal to e to the iz minus e to the minus iz over 2I. So when I add these two together, I'm going to get my integral from p to r, e to the ir, minus, this minus here, e to the ir, both over r. To convert this now to my sine z, I need to introduce a 2i in the denominator, but then I'm going to multiply the outside of my integral by 2i. So now this here becomes sine of r over r dr. I summarized all my work for L1 and L2 into these two lines, and what I was left with at the end was our 2i times the integral from p to r, sine of r over r dr. I'm going to come up here just to review where we got there. We had our integral. This was our closed curve integral. It was the integral over L1, which is, I guess I'll outline it in yellow, L1. Then the next thing was CR. So that was this part of the curve, CR. And then I integrated over L2, which is here. And then over CP, which is this part of the curve. So I have my closed curve integral. I had isolated my L1, L2, and that's what I found to be sine of r over r. And then on the other side of the equation, I just moved over minus my CR and my minus CP. So that's what this is over here, my minus CR and CP. Now looking over here at the CP and CR, on my steps over here, make a closed contour, integral, apply Cauchy-Goursat. First is, according to Jordan, the CR, this path, the big semicircle, that's going to go to 0 as r goes to infinity. And then according to our indented path theorem, this CP, that'll approach minus pi I times the residue of the singularity that we're going around. So that means this is going to go to 0, but for CP, we need to find the residue of e to the iz over z. To do that, I'm going to use the summation formula like we did when we did the Laurent series. We want to look at the Laurent series so we could find the coefficient of the z to the minus 1 power, and that'll give us the residue. So we're going to start again with this series formula for e to the z. Here we're going to look at e to the iz over z. We're going to factor out the 1 over z. We're going to use e to the iz. We plug in iz for z here in the summation formula. So we're going to get iz to the n over n factorial. When n is equal to 0, we get iz to the 0, which is just 1, over 0 factorial, which is 1, so we have 1. When n is equal to 1, we have iz over 1 factorial. When n is equal to 2, we have iz squared over 2 factorial. When n is equal to 3, we have iz cubed over 3 factorial. Multiplying by my 1 over z, I'm going to have 1 over z times 1. 1 over z, these cancel out, so I get I over 1, which is just I. Here, one of the z's cancel out, so I'm going to have my I squared over 2 times one of the z's. But I actually don't need to do any more terms because to get the residue, I just want the term of the z to the minus 1 term, and the coefficient is equal to 1. So I have this note here that e to the I z over z has a simple pole at z naught equals 0 with residue equal to 1. Now, according to my theorem for indented paths, that means the limit as p goes to 0 over cp, this curve that we use to avoid this singularity, is equal to minus pi I times the residue being 1, so it's equal to minus pi I. I'm almost finished, so I'm going to shrink this to give me just a little more space, but I said as our theorem, our integral over cp over here as p approaches 0 is equal to minus pi I. I said by Jordan's lemma, this integral here as r goes to infinity goes to 0. So now that means our integral over cp and cr is equal to pi I. On this side of the equation, I shrank this down, but I had this left-hand side of the equation is equal to 2i times the integral p to r sine of r dr, which gives us the sine of x over x dx. If I divide both sides by 2i, I'm going to be left with pi over 2. And this, again, is as p approaches 0, that's our bottom limit of integration, and as r approaches infinity, and that's the top part of our integration. So this is our final answer. Our next topic is to talk about indentation around branch points. This is the example we're going to do. If you recall, logarithms or natural logs are multi-valued functions, so we often take one branch of the function so we get a singular function. Sort of like when you have square root of some number, let's say 4, you could either have, in complex numbers, the square root of 4 could either be 2 or negative 2, but you might say, I only want to take the positive branch, so in which case your answer would be 2. So similarly, for the natural log, we choose a branch, and when we choose a branch, we limit what our arg or our theta, our angle, will be, and in this case, we're going to limit our theta to be between negative pi over 2 and 3 pi over 2. Our strategy for this indentation around a branch point is very similar to our strategy for indentations around a singularity. We're going to replace f of x by f of z. We're going to note the singularities. We're going to make pretty much the same closed contour integral, and we're going to apply the Cauchy residue theorem. We're also going to use the indented paths as well as Jordan. So we find that the integral around CR is 0 by Jordan. The integral around CP, our indented path, is equal to minus pi I times the residue of our function. And then we're going to equate real or imaginary parts to get our final answer. So let's do this example. So here is the problem. We're going to verify the integration formula. Integral from 0 to infinity, natural log of x over x squared plus 4 squared dx is equal to pi over 32 times natural log of 2 minus 1. Our first step then is to replace f of x by z, and the implication is here this is an integral along the real number line, but now we're going to move to the complex plane. So we're going to consider f of z equal log of z over z squared plus 4 squared, and what we have is in our complex numbers, we have log of z is equal to log. Converting z to a complex number in exponential form, we get r e to the I theta, which we had seen in our video about logarithms, is equal to natural log of r, the radius, plus I times theta, and then this is a multivariable function. In other words, log of r e to the I theta has several values as we keep rotating around the circle, so it's 2 pi n, where n is an integer, multiplied by I. And our book tells us that first we're going to only consider magnitude of z, or the radius, is positive, and it tells us that we're going to limit now our theta, or arg z, to be between negative pi over 2 and 3 pi over 2. So that restrains our theta here, and we no longer have these multiple values. The picture that we have is we're going from this negative pi over 2, but we're not equal to negative pi over 2, which is why I put this red line to indicate that's where our branch cut is. And we do not consider values of z where theta is at pi over 2. So anything greater than pi over 2, and then we go all the way around to 3 pi over 2. And again, we meet at this branch cut. Our next step then is to note our singularities. So the singularities of our function, we're going to look at our denominator. So q of z is equal to z squared plus 4 squared. I'm going to factor this out. This is z minus 2i squared, z plus 2i squared, set it equal to 0, and I see that the denominator has roots at z equals plus or minus 2i. So first of all, let's consider 2i. That is over here, so that's good. But let's also consider our negative 2i. Well, that negative 2i is along our branch cut. So we're not going to be using this singularity because it's not enclosed in our path, because our path does not include the branch cut. But 2i is inside the closed path. Now the next thing I'm going to do is to make the closed contour integral, and I've drawn it here, and it looks a lot like the one we had for just a regular indented path around a singularity. But now this branch cut is over here. I should draw that in red. So our branch cut is here, so this indented path allows us to avoid our branch cut. In particular, this little indentation, without this indentation we'd be integrating along a semicircle, but then we would be including this branch point at the origin. So we need this little indentation around the origin to avoid the branch point. Now for this closed contour, I can apply my Cauchy residue theorem. That's also noted here. We want to apply the Cauchy residue for the entire closed path. The Cauchy residue says that this integral around the closed path is going to equal to 2 pi I times the residue at our singularity of f of z. So I just wrote that here. Our closed path is this L1, our CR, this outer larger semicircle, our L2, which brings us back to our smaller semicircle. So that's our closed path, and that's 2 pi I times the residue of the singularities inside our closed path, and that only includes 2i. So the residue at z equals 2i of f of z. To calculate this residue, I'm going to use this theorem, residues at poles theorem, and this is one we had got from a previous video when we talked about singularities and poles. So if f of z is equal to a function phi of z over z minus z naught to the m, where this z naught is our pole, and we have exactly this form, right? We have phi of z is equal to log of z. Actually, I should back up. So our z minus z naught, our pole that we're interested in is our 2i. So over here, this is our z minus 2i squared. That's this, where m is equal to 2. So what's left for our phi is our log of z, and then also on the bottom in the denominator is z plus 2i squared. And then we will find by our formula then the residue at z equals z naught, in this case that's 2i, of f of z is equal to the m minus 1 derivative evaluated at z naught divided by m minus 1 factorial. I will be also using this formula for derivatives of logarithm that we had derived in a previous video, like way back when we talked about derivatives of complex functions. But what you'll see is the derivative of log of z, and I actually went ahead and I have written out the derivation, but it ends up equaling 1 over z, which is kind of very analogous to what we have for normal calculus. Using this formula now to calculate the residue at 2i, I have log of z over z minus 2i squared, z plus 2i squared. So our phi of z, again, is log of z over z plus 2i squared. I'm going to take the first derivative, right, because here Rm is equal to 2. So m minus 1 is 1. So I'm going to take the first derivative of my phi of z. So phi prime of z, just using the quotient rule, I square what's on bottom, I have what's on bottom times the derivative of log of z. I have this formula here for you, for your reference. It's just 1 over z. And then minus what's on top times the derivative of what's on bottom. And when you plug in 2i into here, what you will get is pi over 64 plus I times 1 minus natural log of 2 over 32. And for your reference, I have the intermediary calculations here. So plugging in 2i, on this part I get 4i squared 1 over 2i, and then I have 2i here to the fourth, and then minus, and of course I have the 2i to the fourth on the bottom, but the numerator then is going to be log of 2i times 4i. Simplifying this, I get 8 over I over 256, which is equal to 8 over 32. Over here, I'm going to pull out the 2 times 4i. That'll be 8i, and then I'm going to pull out my denominator, which is 256. My log of 2i now, I'm going to use this formula here. So to convert the 2i into exponential form, well, the radius is 2, and then let's find the angle for this e to the I theta. Let's find the theta. If I look at this drawing of 2i, theta is equal to pi over 2. So log of 2i is going to be, according to this formula, natural log of r plus I theta. So that's natural log of 2 plus I pi over 2. And then you can see that, what is this? Where does this go? This is 8 over, well, this becomes 1 over I over 32, or I times 32. So that's this part here, the I times 1 over 32. This here becomes, 8 goes in here 32 times. So that's this natural log of 2 over 32. And then this term, when you multiply, you get the plus sign because the i's give you a plus sign. This 8, again, is 1 over 32, and then you have this 2, so this becomes pi over 64. I'm going to get rid of some of this intermediary work here, but I'm going to leave this line about the Cauchy residue theorem and then write that our closed curve integral then is equal to 2 pi I times our residue, which we just calculated right over here. I kind of cleaned up some of my intermediary work I did have where we calculated which singularity is inside the closed path. Here's my closed path. It's equal to 2 pi I times our residue, which then becomes I pi squared over 32 plus pi over 16 natural log of 2 minus 1. I can now take this formula and I can say L1 and L2, the path integrals over L1 and L2 is equal to 2 pi I times our residue minus my path integral, the small path indented part of my path, minus this semicircle on top. Looking at our path L1 then, that's this part here on the positive side of our indentation. L1 is on the real number line, so our theta for any z, any complex number on L1, when you put it into this exponential form, our theta is equal to 0 because we're on the real number line. So z equals r e to the I theta. Theta is equal to 0, which means z is equal to r. And r here then will vary, the radius will vary from p to our capital R. Looking at L2 over here, our theta is equal to pi, so z is equal to negative r, and our radius is also going to vary between p and r. Now we can write our integrals along L1 and L2 as the integral from p to r natural log of r over r squared plus 4 squared dr, plus the integral from p to r natural log of r plus I theta. Now again, this is for L2 over here, over r squared plus 4 squared dr. Combining then our natural log of r over r squared plus 4 with this integral, we have 2 times the integral p to r natural log of r over r squared plus 4 squared dr, plus our I pi gets moved out. Integral from p to r 1 over r squared plus 4 squared dr is equal to, And now we put this in terms of our residue over here. So the residue we calculated for the whole entire closed curve integral minus the integral over our indentation minus the integral over the large arc C sub r. I'm sorry to have to crowd this in, but I'm almost done. So in my equation now, I'm going to integrate my real parts and then I'll integrate my imaginary parts. Equating my real parts, so which terms are real? So this part here are 2 over integral p to r natural log of r over r squared plus 4 squared dr. What else is real? This term here, pi over 16 natural log of 2 minus 1. And then finally we have these two integrals, and these two integrals can have real and imaginary parts. So I'm going to just take the real part of those integrals. And what we are going to show actually is these two integrals go to 0. So that's our next step. So I've cleared all this stuff out so we have room. Where we left off is we were going to show the integral along the indented path and the integral along this upper circle are both equal to 0. What we'll be using is this theorem, which we've seen before, is the upper bound for moduli of contour integrals. So let C denote a contour integral of length L. So in this case, we have two contour integrals. They're both semicircles. It's very easy to figure out what L is because we know the circumference of a circle is, let me write this in blue. Since the circumference of the circle is equal to diameter times pi, we can also say that's equal to 2 times the radius times pi. So we can figure out, again, the length of L. Suppose that a function f of z is piecewise continuous on C, so we have our function, our log is continuous on this curve. And if m is a non-negative constant such that m is always greater than f of z, then for all points z on C, which f of z is defined, then the integral along the curve is less than m times L. So in other words, if you think of integrating as kind of like summing up all the little pieces along the curve, if we know that f of z is less than m and our curve length is L, then because f of z is less than L, then summing up all the little pieces will be less than or equal to m times L. Actually, I should note this is for the entire circle, but because we're talking about just the semicircle, that's equal to r pi. We are going to start with CP, the little indented path, so that's a semicircle of radius p. And if z is on this path, that means z is equal to p, that's our radius, e to the I theta, and again theta here is between 0 and pi. And we're going to assume p, our radius, is less than 1. And in fact, we want it to be infinitesimally small, so we barely make it over the origin, our branch point. Because we're trying to get a bound on our function, we're going to look at our absolute value then of our numerator, that's log of z, and a bound on our denominator, that's z squared plus 4 squared. So let's start by looking at log of z. We convert that to natural log of p plus I theta, which is less than or equal to, by the triangle inequality, natural log of p plus I theta. Here we have minus natural log of p, and I theta is going to be always less than pi because we're going between 0 and pi. Our z squared plus 4 then is going to be greater than or equal to the absolute value of z squared minus 4, which is equal to 4 minus p squared. Now we will look at the bound of the real part of our integral. It's less than or equal to then our integral, just the entire integral, f of z dz, which is less than, we're going to plug in our numerator, our bound for our numerator, and our bound for our denominator, times our length, in this case using our upper bound for moduli. Our length again for this semicircle is going to be pi times p, and this then gives us our bound here for our real part of our little indentation. And what we want to remember now is our p, our radius, gets infinitesimally small. So the limit as p approaches 0 of this pi times pi p minus p natural log of p over 4 minus p squared will give us, over here, the bottom approaches 4 and the top approaches 0, so our limit is equal to 0. And that's the first thing we wanted to show. We wanted to show that the real part of our integral around our indentation is equal to 0 as p approaches 0. We can do something similar for this part of the semicircle C sub capital R. So the real part, we find a boundary is equal to pi over r plus natural log of r over r squared divided by r minus 4 over r squared. We need to use L'Hopital because as we let r approach infinity, we have infinity over infinity, so we take the derivative, and then we eventually get 0. So we show this as well. Going back to our original problem, this is where we left off, where we were showing then that this integral around the little indentation, the integral around the big semicircle is equal to 0, but I'm just going to review where we went. So first we found that 2I is our singularity inside the closed path integral. We used the Cauchy residue theorem to find the integral along the entire path. Then we said that the integral along L1 and L2 along the real lines is equal to our entire path minus the integral along our indentation minus the integral around C sub r. We just found that these two integrals along the indentation and C sub r go to 0 as p approaches 0 and r approaches infinity, but looking at L1 and L2 we had done previously, we combined these two so that we got these are equal to 2 over or 2 times the integral p to r natural log of r over r squared plus 4 squared dr plus I theta integral p to r 1 over r squared plus 4 dr. And that's again equal to our residue from our residue theorem. These two here go to 0. So now, equating just the real parts, what we get is that our integral from p to r, p is approaching 0, and as r approaches infinity, of natural log of x over x squared plus 4 squared x is equal to, now we can divide both sides of this equation by 2, and we get 1 over 32 times natural log of 2 minus 1, which is exactly what we wanted to show. And one thing I do want to just emphasize here, when we showed that C sub p goes to 0 as p goes to 0 and C sub r goes to 0 as r goes to 0, what we used was the upper bound for moduli of contour integrals theorem. I also want to note, if instead of equating the real parts, we had equated the imaginary parts, we would have gotten the integral is equal to pi over 32, but that's just another integration formula, so that would have given us another valid result. In this video, we talked about indented paths and indentation around a branch point. First, we looked at indented paths. So we had this theorem that said, suppose we have a function f of z, which has a simple pole, x naught, on the real axis. So this is important that it's on the real axis. And there's a Laurent series representation in a punctured disk. This is this dotted circle here. So everything interior to the circle, with the exception of our singularity x naught, and with residue b naught at this point x naught. Now if CP, this is this little semicircular path, denotes the upper half of a circle with radius p, where p is going to be equal to r2, it's going to shrink down to 0, so it just barely kind of goes around our singularity. Let's see, in the clockwise direction. Then the limit as p approaches infinity of this C sub p, this little indentation around our singularity, will be equal to minus pi I b naught, our residue. We then use these indented paths to take an improper integral with the singularity on the real axis, and our example was the integral from 0 to infinity, so along the real axis, of sine of x over x dx. Our first step was to move this into the complex plane, and certainly the real number line is a subset of the complex number, so we can do that. We replaced f of x by f of z. Second, we noted the singularities along the real axis. Next, we replaced any sines or cosines that are in our function with e to the iaz. We made a closed contour integral, and then we applied the Cauchy-Goursat theorem. So here we have a closed contour integral, which we can apply the Cauchy-Goursats to say that if there are no other singularities here, then the integral along our closed contour integral will equal to z. So the integral around c sub r then is equal to 0, and the integral of c sub p over here is equal to minus pi I times the residue f of z. That comes from our theorem of indented paths. If the integral was with sine, we take the imaginary part. If it's with cosine, we would take the real part. In this case, our function had a sine, so we would take the imaginary part, and we worked this problem out in full in the main part of our video. Next, we use the indented paths to take an integral around a branch point. And as our example, we looked at the integral from 0 to infinity, again along the real number line, of natural log of x over x squared plus 4 squared dx. And the thing about natural log is it is a multi-valued function. In other words, once you find a solution for whatever natural log of x you have, the solution, you can just add 2 pi I to it and have another solution. So sort of like, square root of 4 is multi-valued. It could be positive 2 or negative 2, but we could limit that and say we're only looking at positive numbers or solutions for square root. In the same way here, for our multi-valued function of natural log of x, we can limit it and say we're only looking at solutions when the argz, or the theta, when you convert x to a complex number, that the theta can only be between negative pi over 2 and 3 pi over 2. So that would be negative pi over 2 here up to 3 pi over 2. So it's this branch here, and our cut is this line here in red from 0 down the negative axis. And that will make our function a single valued function by focusing on this branch. We could have chosen another branch, but for this we're choosing this branch here. And now that we have this branch cut, we don't want our integral that's along the real number line to hit this point at the origin, because it's part of our branch cut. It's a branch point. So we need to avoid the branch point, so we have this indentation. The steps we take are very similar to the ones we had for improper integrals with singularities of a real axis. We replace f of x by f of z. We note the singularities. In our example here, we actually do have a singularity in our closed curve integral. If we didn't, we could use Cauchy-Goursats like we did in this example. But we do have a singularity, so we need to apply the Cauchy residue theorem. Now that we have a singularity inside, that means the closed curve integral, and the closed curve is composed of L1, the CR, the L2, and the CP. So these four curves added together gives us a closed path integral, and by Cauchy, that's equal to 2 pi I times the residue at our singularity of f of z. The next thing we did is we used this theorem, the upper bound for moduli of contour integrals, to show the integral along CR approaches 0 as r approaches infinity, and the integral along CP approaches 0 as p approaches 0. And this is the theorem we used, and then finally we equated real or imaginary parts. This was kind of a long video, but we're at the end now. Thank you for watching.